Davy Stevenson. She has a Twitter account for both of her cats. They are Kamaji-kun and Twistiny-Wiston. I find this very impressive. I only have one Twitter account for my cat. Davy's going to be talking to us about Ruby as science and art, as in art and craft, which is good because every time I'm programming, I feel like I'm gluing macaroni to a piece of paper. So I hope that I'll be able to learn something from this. All right, glitter too, yes. All right, thank you. Everyone, please welcome Davy.
So my name is Davy Stevenson. My Twitter handle is up there and all of that. So the goal of this talk is for everyone to walk away with something new to think about, whether or not they think of themselves as a computer scientist, whether they think of programming as an artistic medium, or whether they think of programming as their craft. I work at Esri in the Portland R&D Center. So Esri is the premier producer of GIS software. They're also kind enough to say yes to my request of sponsoring this conference because I love Ruby on Rails so much. So thank you very much, Esri, for allowing me to be here and the rest of our Ruby team, Ken and Jen back there. I work on the GeoTrigger service, which is a product that Esri makes to help make geofencing more accurate and easy for mobile developers to add into their apps. I'm not going to be talking anything about the GeoTrigger service in this talk, so if you want to know more, feel free to come and ask me about it later. So for those of us who have a degree indicating that we have formally studied the discipline of our careers, that degree most likely says computer science. One of the newer scientific fields, the structure interplay of the computer science department can drastically differ between different colleges and universities. Computer science was born out of mathematics, but has a physical component that mathematics lacks. The physical properties that control the function of computers, they also encourage study along other fields such as physics or electrical engineering. Some programs continue the tradition of having lab classes. Others can be mostly theoretical. It is entirely possible to graduate with a computer science degree without actually having written any code. So if students aren't actually learning code in computer science classes, what exactly are they learning? One of the fundamental classes for any computer science major is the study of algorithms. Studying algorithms abstractly, that means devoid of any programming language, encourages us to divorce the implementation details from the underlying properties of the problems that we're trying to solve. Algorithms are analyzed by their overall complexity, which is also known as big O notation. What we're trying to determine is how well does the algorithm scale. An algorithm is almost always fast on a set of 10 elements. What happens if you have a set of 1,000 or 10 million? So here's a graph showing how the algorithm running time increases as the number of elements increase for a variety of the major big O notation complexity designations. When you're analyzing an algorithm for big O notation, all we care about is the highest order factor. We ignore any constants or any lower order terms. So O log n algorithms grow very, very slowly. You can barely see that the bottom blue line is even increasing at all. Generally, this means that the algorithm is running on a set of sorted data. We can assume this in our algorithm, and that allows us to make these algorithms run very, very quickly. This is why caching and pre-sorting our data is so important. ON algorithms require a distinct analysis of every single point in the set. ON log n complexity encompasses the vast majority of the best search algorithms. So we know that this is incredibly important to us so that we can then later have quick O log n algorithms to run the analysis on that sorted data. Next, we have the O n to the c algorithms, known as quadratic when c is 2, otherwise known as polynomial. I've only shown the n squared here. These algorithms are where we're starting to get into the realm of rapid growth as the number of points increase. OC to the n algorithms are exponential, and they pretty much require either a known small data set or processing via background tasks. The exact solution to the traveling salesman problem is an exponential algorithm. So now we get to the real bad boys, O(n) to the O(n) bang factorial. You're going to have a bad time if you try and implement any algorithm that's a factorial algorithm. You are going to run into pretty major problems very quickly as your data sets scale. So if you want to know a little bit more about these, there's other resources available. So the Big O cheat sheet is a great site. It has a ton of different space and time complexities for many of the common algorithms, and they show like many different algorithms that solve many of the same problems. There's also the algorithmics, which I find hilarious. So this is basically a dance troupe that displays many of the common sorting algorithms via various dances, including Hungarian dance. Highly entertaining. I recommend watching them. So what is an algorithm exactly? It's a set of instructions that solve a particular problem. A problem might have many algorithms that describe correct solutions, and many, many more that describe good enough solutions. I'm going to talk about one particular problem. Convex hull is a mathematical term to describe the envelope of a set of endpoints. Easiest heuristic for imagining this is to think of wrapping a string around the set of points. This is a really bad example because this person obviously doesn't know how to wrap string around points to correctly delineate the convex hull, but it is a much prettier picture than many of the others. The points that the string touch are the points on the convex hull. And it is true that all the vertices creating the polygon that define the convex hull consist entirely of points within the set. This is an important thing to prove mathematically before trying to solve these sorts of problems. So convex hull is really useful for a variety of different tasks. This includes in computer graphics if you want to do more advanced bounding box calculations, for quicker intersection calculations. It's used for pattern recognition, image processing, and in GIS. Finding the convex hull allows for many other further calculations as well, such as finding the centroid or center of gravity of the object, or, as I mentioned earlier, doing any intersections with other polygons. So the brute force algorithm to solve the convex hull problem, involves iterating through every single pair of points. For even a small data set, such as the Pleiades here, this is a lot of lines. I gave up drawing after a while. There's way too many lines to even attempt drawing even in this small set. So the brute force algorithm takes advantage of a simple fact, which is that for any line that is on the convex hull, all of the other points in the data set are going to be on only one side of the line. A line that is not part of the convex hull will have points on both sides. So with this simple fact, as you're iterating through all of these sets of lines, you can calculate, again, all the other points. Are they all on one side, or are they on a mixture? And then pick the ones that are on that convex hull. So what's the ON designation of the brute force algorithm? So first we have to go through each pair of points, which is ON squared. Then for each one of those, we have to determine if the other points are all on one side of the line, which is another ON designation. Since these two things are within each other, two nested loops, that means the total running time is ON to the third. And we can do a lot better than that. Another relatively simple algorithm that has a huge performance boost over the brute force is known as the gift wrapping algorithm, or Jarvis March. First, you need to find a point that is known to be on the convex hull. That's pretty easy to do by iterating through all of the points and finding the leftmost point, or one on one side of the edge. Now that we have this one point, we can iterate through all of the other points and calculate their polar angles with respect to that vertical line that we've drawn. After we've found the polar angles of all these points, we just need to pick the one with the minimum polar angle. We found the first line on our convex hull. This process can repeat. So now we have a new point. We will calculate the polar angles for all of the remaining points with respect to this new line. Again, pick the smallest polar angle and continue working around. So you can see why it's called the gift wrapping algorithm, because we're pretty much literally wrapping the set of points as we go along. Once we get back to the first point again, we know that we've completely wrapped the set. We found the convex hull. So what's the ON designation of this algorithm? So first we have to find that one edge, and that's an ON calculation, but it's also not within any other loop, so this is kind of a plus n at the end of our calculation at the end. Then we're going to calculate all the polar angles, which is another ON algorithm. We have to repeat for each point on the hull, so h is the number of points on the hull. So that means that the total algorithm is n times h. In the worst case scenario, if every single point is on the hull, then that means this is an ON squared algorithm. So that's a pretty significant boost over the brute force. There are some other algorithms that are useful for when the convex hulls, for different data sets. Like if the number of points on the hull is expected to be very, very large, then you can switch over to using a slightly more complex algorithm called the gram scan. This is an ON log n algorithm. There are also at least 8 other algorithms that have been discovered in the last 30 years that solve this problem in ON log h. The most appropriate algorithm for any given task depends on the expectations of the data set as well as the expected outright cost of and maintainability of the algorithm. Using a very, very complex algorithm that runs very quickly might not be worth it if you're not using it a lot or if you don't want to spend the programming time, maintaining that algorithm over time. So these faster algorithms might not be worth their implementation cost. So the field of computer science strives to find more efficient algorithms to many of the common problems, and also to find ways to solve new problems with the existing algorithms that we have on hand. So whether or not you consider yourself a scientist, the code that you write and the tools that you build can be used to further our knowledge of computing. So it is a common idiom within the Ruby community that we love Ruby because of its beauty and its expressiveness. This sentiment comes from our artistic selves, that our programming language can be seen as our medium. Ruby as a medium is both flexible, powerful, and elegant. So we talk about the beauty of code like we talk about the beauty of a painting. The structure of the different components, the skill and artistry of our methods, the impressive feeling when we step back and watch all of these pieces working together in harmony. If Ruby is our medium, then our syntax choices and our method structure, our coding guidelines are our artistic style. There are Rubyists that subscribe to a minimalistic style, and others who prefer to decorate their code with qualifiers and quantifiers to make their intentions explicitly clear. Ruby pushes an object-oriented style aggressively, but you can also take a more functional approach. Our style becomes our identifying trait. Neuroscientists are discovering that the pathways in the brain that light up when someone views a beautiful painting or listens to music that they find particularly moving, these same pathways light up when a mathematician views an equation that they find particularly beautiful. This is Euler's identity, which is considered by most mathematicians to be the most beautiful equation. This is because in addition to containing all of the basic mathematical operators, it contains addition, multiplication, and exponentiation. It also contains additive and multiplicative identities, 0 and 1, and the most important numbers in trigonometry, natural logarithms, and complex numbers. It's pi, e, and I. I think that if neuroscientists looked at the brains of computer scientists, when we viewed code that we find beautiful, we would see those same pathways light up. Unlike many other artistic endeavors, we do not have the luxury of coding by ourselves in a vacuum. Programming is by definition a social activity. We write software on teams, and our software that we write depends heavily on other libraries, frameworks, and tools written by a vast community of programmers. As artists, we need to know how our artistic style impacts the people that we're working with. Our style can help or hinder the teams that we work with. We create coding style guidelines for a reason. It is really difficult to complete a work of art with many divergent styles. So does this mean that all of us should coalesce down to a single style? Well, I think that would be incredibly boring. It'd be about as exciting as a museum with a single painting. We are benefited by the ability to solve problems in many different ways. by thinking about the issue from many different angles and by implementing different algorithms. And so we should celebrate these differences that make us unique, to encourage our community of Rubyists to be free to try new things, to solve new problems. So we should encourage them to go down new paths. Also, do not make the mistake in thinking of something complex as something that is not also simple. Complex problems require complex solutions, but each particular component should be the most simple solution to the problem. The simplest cog that fits the machine. Art is about simplicity, and code is about simplicity. We espouse dry code. We rejoice in the single responsibility principle. We package our code into libraries and frameworks. This is all about simplicity. To become a master craftsperson takes time, practice, and skill. This was codified into the idea of apprentice, journeyman, and master designations. Theoretically, anyone with enough practice could climb these ranks. If we are craftspeople, or artisans, then this might shake up some of our previous assumptions about the innate abilities of people required to write code. We should think about programming as a set of complex skills that take years to master, but with enough practice, anyone can do it. I think it's fitting that the very first computer was actually a loom, and it was used to create even more beautiful fabrics. I'm a knitter. I've gotten to the point where I feel extremely capable with a variety of knitting-related skills. I've enjoyed mastering these dozens of advanced techniques over the years, even with all this previous experience. When I'm learning a new technique, I'm often starting over as a beginner again. Yes, my expertise makes it easier to understand the instructions. My built-in muscle memory might make it easier to pick up the new motions that I need to make. But many times the current skills do not map 100% to the new thing. And this is the glory, right? The fact that even as experts, we're continue learning and growing, even in an area that you feel mastery. Knitting is just knit stitches and purl stitches, just like programming is just zeros and ones. Okay, great. That just sounds really easy. Where do I start? Wait, there's how many different cast-on methods? Pretty soon, you are knee-deep in technical jargon. Swap these stitches with those stitches on needles, and you get cables. And how exactly am I supposed to, add more stitches? Oh, wait. They make those lacy holes as well. Once you figure out, you can make some really cool things. And then you learn about steeking, and all of a sudden it's, what do you mean I have to cut my knitting? I just spent hours making this. That's sort of how I felt when I learned functional programming as well. Initially, all knitters start out only being able to follow the patterns exactly as they're written, which, by the way, is another really great thing that knitters provide, which is instructions in multiple different formats. There's written instructions for the verbal folks, charts for the visual, and copious YouTube videos for when you need to watch something 17 times in a row in slow motion because you really can't figure out what the heck they're doing. In many ways, following these instructions, these algorithms, means that you are the program running this program, Make Sweater. As long as you don't deviate from the course, at the end of the algorithm, you will, in fact, have a sweater. Eventually, though, you start to feel a little bit constricted and want to fiddle with how all the parts work underneath. Since you were here at this conference, I have a feeling that you might be one of these people as well. Maybe your proportions, or the proportion of the lucky person that you're knitting for, isn't matching the exact proportions of the person who wrote the initial sweater algorithm, so it's not algorithm. Maybe your arms are a little bit longer. Perhaps you want a different cast-on method that you prefer, has some extra benefit that you like over the one that the pattern has by default. Maybe you want to swap out the design, add a little detail here or there. Once you've mastered all the various algorithms and sub-algorithms of knitting, this is pretty easy to do. Now you are the algorithm creator, not just the computer. Even though I'm a knitter, sometimes knitting can't solve a problem that I want it to. I'm not usually a fan of crochet, but when it's the right tool for the job, then you can't argue with that. If a sweater needs more support at the shoulders or a nice decorative hem, then crochet is the right answer. Or maybe embroidery. It's my craft, I can choose the best tool for the job. And by exploring other crafts and seeing what they have to offer, my final product is going to be improved. Craft can be a profession, but it can also be a hobby. I find it interesting that we as programmers also follow this model. We have a tendency to make our work our hobby as well. We like to create silly things that go alongside our serious endeavors. We create things to bring happiness to others. And I don't think that this is a coincidence. Getting paid for our time is a nice perk, but at the end of the day, we write code to enrich the lives of others. The most important thing is for our work to be used, to bring happiness to other people, to create things so that they can be enjoyed. So I ran an experiment where I asked the internet for examples of beautiful code. I did not specify exactly what I meant by this. I left my request pretty vague on purpose. I wanted people to fill in the blanks with their own ideas of what beauty meant. I got a lot of answers. Some were serious, and some were silly. I'm going to go through pretty much every answer that I got. Some of these answers were projects that many people know and use on a daily basis. Code that does a lot of our heavy lifting for us. These projects succeed because the team working on them has a vision. They are projects that are well organized, well documented, well tested. Other projects you might not have heard of, they might attempt to solve difficult or common problems, but maybe with a slightly different approach. The coding styles of particular people were highlighted. Chris Maddox commented that SF Eric's work on OAuth 2 was the basis for every gem he builds. Can we get this guy a Ruby Hero Award yet? Come on, look at that, look at that. Sometimes beautiful code is not about the code itself, but about the clean API that it provides. Wrapping a core piece of technology that might be perhaps difficult to use in a way that's more easy to understand and use, that's rewarding, and can make the lives of many other programmers much easier. Beautiful code might be the extension to a language that it makes. So what does this code do exactly? Let's look. So the two main things. It adds not to object. What does not do? Not class. All it does is have a method missing and then put a bang on the front. So what does this give us? So we can write code like this. Is nil not nil? No. Is 1 not equal to 2? Yes. It's kind of fun. I like that Ruby can do that. Fun things are beautiful. This is hilarious code, by the way. You should check it out. This is also some fun game. You should try this. I played it for like 2 hours once I actually got it installed. It was great. What is it? Just making a little Ruby man hop through some hoops. Flappy Bird style. Come on. It's great. It's like one file. Read it all. It's great. I also found the most perfect code. You ready for this? Let's see what's in perfectcode.rb. And the best part is that even perfect code isn't perfect the first time. So I thank everyone who gave me solutions or gave me answers to what they thought was beautiful code. I had a really great time with that. And so what did we learn exactly? So we learned that beautiful code comes in many different shapes and sizes. The beautiful code can be the big, heavy projects that do lots of heavy lifting, solve complex problems that we use on a day-to-day basis that we rely on. Beautiful code is collaboration. It's about the people that we're working with and the teams that we're on. Beautiful code allows other people to write beautiful code. And beautiful code is just fun and simple. If programming is a science, then we should always be looking to expand our collective knowledge. And we should be excited when others create discoveries. Diverging when solving a problem is a good thing. Exploring multiple paths, finding out what's down there, and then coming back and bringing the best results together in the end, that's what science is all about. That's what's going to move us forward. If programming is art, then we should admit that there are many right answers. and admit that others have different artistic styles, even if we don't like them. They're still right. Rather than being divisive, this adds beauty and interest to our community. It makes our community more welcoming and open, no matter what their particular style is. If programming is a craft, then we should know that the particular tools that we choose to solve our problems are not really relevant to our overall existence as craftspeople. Yet in many ways, they will drive our final result. The way that we solve problems as Rubyists is going to be very, very different than if we were writing in Java or Python or C. Even the differences between Rails and Sinatra or Node. We can learn from other languages and other frameworks. We can take advantage of their benefits when they're the right tool for the job. If our community continues to think about these things as we write our code and interact with the other people around us, then everyone's experiences will be improved. All of us are here today because we have already mastered the determination to wrangle computers. Let's make sure that we're practicing our skills of empathy and communication as well. Continue to help others enter our community and further their own skills. What's almost as good as finding out that someone already wrote the code that you need? Mentoring and encouraging someone new so that they can write code, so that later on down the line, when you're reaching for new code again, see if someone solved that problem, finding out that that person that you mentored is the one that wrote that code that you now need. Nothing beats that feeling. Tech is not a zero-sum game, so let's work together to build our future together. Thank you very much. Thank you to the guys for putting on such a great conference. Thank you to Eric, Jenna, and Jen for providing me many fine images to use in this slide deck. And thank you very much, Esri PDX, for being awesome and coming with me to this conference.